Hello everyone, I'm Lirui. Today I'll be presenting Does Learning from Decentralized Non-IID Unlabeled Data Benefit from Self Supervision? This is a joint work with Kaiqing, Yunzhu, Yonglong, and Russ from MIT CISA. Machine learning algorithms heavily rely on absorbing a large amount of data. This data are naturally generated and stored in a distributed fashion, such as in self-driving cars, warehouse robots, and mobile phones. Taking the Amazon warehouse, for instance. There's a fleet of robots that are doing logistics every day. The package density of the warehouse heavily depends on the robot size and locations and days in a year. Some sites might have only yellow packages, some might have only white, and some might have a mix. In fact, we could have had a distribution of package density across the sites. If we're in face of data from many different warehouses, it's of question to understand whether and how we should pull data. Non-IIDness is a central topic for decentralized learning, where communication budget is limited. Assume there are k local data sources, D1 through Dk, in the federation D. We can generate non-IID datasets for each data source, represented by each circle, sampled from a Dirichlet distribution with parameter alpha, where each color represents a class in a classification task, for instance. As we can see, when alpha equals to 5, each data source has the uniform classes, and therefore the non-IIDness is low. When alpha equals to 1, each data source has skewed classes, and therefore the non-IIDness is higher. When alpha equals 0.01, each data source has only data from 2 classes, and therefore the non-IIDness is very high. We therefore has a knob to control how much non-IIDness we want in the experiment. We also have parameters E to control the communication frequencies, i.e. the number of epochs each local data source would have updated before the next round. Finally, participation ratio, which determines how many of the agents will be randomly sampled at each round. The default setting we use is fed average with SimClear for pre-training and linear probing for evaluation. For comparison, we denote the normal version of decentralized learning as DECA-SL in a scheme that uses decentralized learning to learn a representation network as DECA-SL rep. And finally, we propose decentralized self-supervised learning as DECA-SSL. Our work studied the question, does learning from decentralized non-IID unlabeled data really benefit from SSL? We hypothesized that SSL, compared to SL, learns a relatively uniform and robust representation that's less dependent on the data labels and inputs. We first show the upper bound performance of centralized SL and centralized SSL. We now see that for DECA-SL, the performance drops significantly when we increase the non-IIDness. However, the SSL performance is much more robust to non-IIDness. Specifically, the flat curve for the green bars shows that DECA-SSL is robust on the CFAR10 dataset. It even performs on par with the centralized counterpart that requires extensive communication and storage. And this holds true for both label non-IIDness and feature non-IIDness. In addition, we conducted experiments with changing communication epochs, shown in the x-axis. DECA-SSL shows much better robustness than SL representation, and similarly for partial participation ratios. In other words, DECA-SSL is more robust when less data sources participate at each round or when data sources are communicating less often. We also did experiments on ImageNet pre-training and tests on detection and segmentation on MS-COCO with ResNet 18. We first showed that the performance with no pre-training. We see an improvement with centralized SSL pre-training. We also see an improvement with decentralized SSL pre-training, and the improvement is on par with the centralized version and also outperforms the decentralized SL version. We also did some experiments on the new Amazon dataset and have found a similar improvement with DECA-SSL pre-training that almost matches centralized SSL. We show some visual results of the segmentations. In addition to our empirical observations, we also provide theoretical analysis of the decentralized SSL and SL rep setting. We construct a 2K-way linear classification problem where each client has majority of their data from only 2 classes on one axis and some sparse data from other classes. We show that the feature matrix learned with DECA-SSL is more uniform among the non-ID datasets compared to DECA-SL, and this is desirable for the averaging in the decentralized case. Finally, we developed an algorithm called FitArc that leverages iterative feature alignment and clustering. At each communication round, we cluster local models into multiple global models based on the feature similarity. We also added a regularization between the local models and the cluster models. And here's another iteration. This prevents local models from drifting too much in the decentralized setting, and we outperform several baselines and related works, as well as showing more robustness to the non-IIDness.